Okay, number 45, they've given you a definite integral here from -2 to 3 of absolute value of x cubed. Now, right away, that should concern you a little bit. We've talked about how the fact that anti-differentiation or even a definite integral of an absolute value function is a tricky thing to do because it's an unnatural function that follows different sets of rules for different values of x. Now, furthermore, I've told you guys to evaluate all definite integrals with absolute value by graphing, but that's really only worked when the function inside the absolute value was linear. So this one's a little bit interesting right here. They want us to write this as the sum of two integrals without using absolute value and evaluate that. So I think it's probably a good idea if we graphed this function here real quick, just to get our sense of what was going on here, guys. Okay, so the absolute value of x cubed, well, you guys know, hopefully, what the x cubed graph looks like on its own. It passes through the origin, and on the right side, it shoots up quickly. It looks like a parabola, but it's actually steeper than that. Now, the left side of this, you'll notice I'm going to do this with a dotted line, would move down into the third quadrant like that. However, the absolute value of this function is going to take any part of this graph that is below the x-axis and reflect it back up over the x-axis. And what that means then, guys, let me undo my last two pieces, is that that left side of this graph is now going to flip up here and look something like that. So what we have here in blue is the graph of y equals the absolute value of x cubed. It ends up looking a lot like a parabola, but it doesn't follow all those little things that parabolas have about its foci and its directrix and all of that fun stuff. So what they wanted us to do with this problem was to rewrite this integral now as a sum of two different integrals without absolute value. So we're going to write this as one integral plus a second integral. And I'm actually going to do the second integral first because I think it's easier. The second part of this, by the way, I'm sorry, this region here is starting at -2. Let me label that, and ending over here somewhere at 3. So I think you guys can see that what I'm shading right here is going to be region number 1, integral number 1, and this one is going to be the region and integral number 2. So like I said, that right side is easier. The second region here starts at 0 and ends at 3. And we'd be taking the integral of the function absolute value of x cubed, but the absolute value is irrelevant there because we know that all of our x values on this interval from 0 to 3 are already positive. So you can just ignore the absolute value then. This is where it gets tricky though, guys. For the first region, the one over here on the left, we'd integrate this thing from -2 to 0. And now the fun part here, guys, if I were to draw just this curve right here and say, okay, what curve is that? If I were to continue it down here, what I have in purple is actually the graph of y equals the opposite of x cubed. So that actually is the function that we're integrating here on the left. That gets you the rest of this curve right up here. So that's how we would evaluate this one. Okay, you actually have to use two different functions when your integrand involves absolute value. So they want us to go ahead and evaluate this thing as well. So let's get to it. Antiderivative of -x cubed is going to be a -1/4 x to the 4th, evaluated from -2 to 0. And we'll add to that 1/4 x to the 4th, evaluated from 0 to 3. Okay, so what are we going to get here? I'd pull the -1/4 out in front, and then in brackets, put the 0 in here to get 0, minus, and now the -2 to the 4th, which is going to be positive 16. So a -1/4 times a 0 minus 16. Plus, I'll do a 1/4 here, start brackets. 3 to the 4th, I believe, is going to be 81, minus 0 to the 4th, which should be 0. What does that do for us, guys? -16 times -1/4 is 4. And we'll add to that, this is unfortunate, 81 over 4. And I guess if I wanted to simplify my answer, I would think of this 4 as a 16 over 4. Add that to the 81 over 4 and get 97 over 4 for my answer for problem number 45. So it is possible to do a definite integral by hand when there's absolute value involved. You just have to make sure that you split it up carefully at wherever the vertex, or wherever this thing changes direction, which in our case right here was 0. But then you have to realize that the equation changes on each side. It was y equals x cubed over here on the right, but it was it was y equals negative x cubed over here on the left.